All right, here we go. Welcome back to part 2 on comparing derivatives. So today, in this example, in this video, we're going to take a look at a derivative again, but at the very end, we are going to sketch what the function actually kind of looks like. It's pretty fun to do. So here we have a function that's closed on the domain 0 to 6. And then they give us these values right there. We'll talk about those later on. Then they say also let f prime of x be continuous and shown in the graph below. So again, this is my derivative. And what do we know about the derivative? Above, we have a positive slope. Below, we have a negative slope. And in the middle, who's my slope in the middle? 0. That's our critical number. So for the first question, we want to find out where we have relative maximums and minimums. So we're going to find our critical numbers because this is our first derivative test. That's our first derivative test. So my critical numbers where the derivative is 0, and I can get those. It looks to be 0, 2, 4, and 6. So when we do our sign charts, going from 0 to 6, f prime and f, we're going to get 2 and 4. We're looking at the signs because this is my derivative. So between 0 and 2, we're above, so that means the function is increasing. Between 2 and 4, we're negative. The function is decreasing. Between 4 and 6, again above, where it's increasing. So we can say we have a relative max, I'm going to abbreviate this time, at x equals 2, and that's because the derivative goes from positive to negative. And we have a relative minimum at x equals 4, and that's because the derivative goes from negative to positive. Easy peasy. All right, for the second example, they're talking concavity. So again, this is our concavity test. We're looking at the second derivative. So if I go up to the graph, I want to find my possible points of inflection, my PPOIs. This is where the second derivative is 0 or D and E. But remember, we're given the graph of the derivative, so we are looking at the slope of the derivative here. Looking at the slope. So that looks like it occurs here. Oh, look, up there my slope is 0, so that's where my second derivative is 0. Also at 3 and 5. And I can find those pretty quickly. That's going to give me 1, 3, and 5. So when we do our sign chart, again, going from 0 to 6, F, and we have 1, 3, and 5. And remember, we're looking at the slopes this time. So between 0 and 1, the slope is positive, just like we did in the previous video. So that's going to tell me that the derivative is increasing or that the function is concave up. Between 1 and 3, my derivative is decreasing, which means that the function is going to be concave down. And here the slope is positive, concave up, negative, concave down. So we can say we are concave up, and again, I'm going to abbreviate this time, concave up on the domains 0 to 1 or 3 to 5, and that is because the second derivative is positive, and we are concave down on the domains 1 to 3 or 5 to 6, and that is because the second derivative is less than 0. Piece of cake. Next one, where do we have points of inflection? That's easy. The points of inflections are at 1, 3, and 5. And that is because two reasons. 1, the second derivative is 0 or D and E, and 2, the second derivative changes sign. That changes our concavity there. All right, so let's get to the fun part. Let's sketch a possible graph, see what f looks like. Remember, this is my derivative graph. Now, if I notice, what this is telling me, between 0 and 2, I know that the function is increasing. On 0 to 2, we know f is increasing. On the domain 2 to 4, because we're below, we know f is decreasing. And between 4 and 6, we know f is also increasing. So I kind of have an idea that the function is going to go up, and at 2, it's going to turn around to decrease, and then at 4, it's going to go back up again. So I kind of have a rough outline of what the graph could look like, but we could do better than that. So let's take a look here. To sketch a graph, the first thing you're going to need is a bunch of points. Hint, they gave you those. They gave you all these points. 0, -2, 2, 5, and 6, 0. So I'm going to just list those out. 0, -2, 2, 5, and 6, 0. The next thing I'm going to want to find, are there any maximum or minimum values? So I'm going to find those. I do have some maximum and minimum values. I found those. We have a max at 2, and we have a minimum at x equals 4. Next, I want to find any POIs. Notice I'm just listing out a bunch of points. Where do they occur? And my POIs, they occur at 1, 3, and 5. And I'm going to graph those. That's what I'm going to do. I'm going to graph those. I'm going to start with any points I have. 0, -2, 2, I'm going to count to 6. 1, 2, 3, 4, 5, 6. 2, up 5. There we are. And then 6, 0. And now I'm going to graph my maximum and my minimum values here. So my maximum occurs at x equals 2. Oh, I already have that point. I don't need it again. But I have a minimum at 4. 1, 2, 3, 4. So 4 is a minimum. So it's a minimum value. I'm going to drop below. I can't drop below -2, though. Okay, I can't drop below -2. I mean, I guess I could if I wanted to, but I'm not going to in this case. So what this tells me is I kind of have a rough outline of what the graph looks like. It goes up, down, and then up, which is kind of what we speculated up here. Now I'm going to graph my POIs. My POIs occur at 1, and on that dashed line, I'm just going to draw a POI here. At 3, there's another one, POI, and then at 5 is a POI. Now, why are POIs so important? Because they tell me concavity between 0 and 1. I know the function's concave up. So I'm going to draw a concave up. Now, I'm not going to go bubble butt down. Don't go bubble butt down. That creates something weird, a minimum, which we don't have. So it's going to be concave up. POIs are where the concavity changes. So the next two has to be concave down. Between the next two, concave up. And then we have something concave down, like so. Again, it's going to be concave down, but I don't want to draw a bubble butt. I want to avoid that here because it creates a maximum that doesn't exist on my sign chart. We would have a maximum between 5 and 6. But between 5 and 6, there is no maximum value. Otherwise, it would show my sign chart at 5 going up and then down. And since that doesn't occur, that's what a graph looks like. Pretty cool to do. All right, next one. Given the function, for what values of k does f of x have a critical number? Anytime we deal with critical numbers, we're dealing with the first derivative at x equals 2. This is easy. So we're going to take the derivative. 6x minus 2kx. And if it's a critical number, at the derivative at x equals 2 has to be 0. So I just find f prime of 2 and set that equal to 0. Plug it in. I get 12 minus 4k equals 0, or k equals, what's that going to become? What's that? Is that 3, I believe? And there we go. Pretty cake. Piece of cake. Easy as pie. So easy, even a student in May can do this. All right, let's go to the last step. Okay, these are fun to do. Ready? The graph of a twice differentiable function f is shown below. Which of the following is true? They're comparing these. That's all they're going to do. Anytime they're comparing, they want to compare the signs. So I need to find the sine of 2, the sine of the derivative at 2, and the sine of the second derivative at 2. Remember, this is just my value. Well, the value at 2 is just 0. The derivative, that's my slope. And at 2, I know the slope is negative. It's going down. And here's concavity. Well, at 2, it's concave up. So it's positive because it's concave up. So I just put them in order. Well, what's the smallest? F prime, then what? F, and then what? F double prime. Well, which one matches that? F prime, F double prime. It looks to be B. As in, boy, that was easy. And then on our last one, let's take a look here. This is the graph of the derivative. Which of the following could be the function itself? So there's a couple of ways I can do something like this. Obviously, option 1, I can look here. If this is the graph of the derivative, this is saying on the domain, negative infinity to 0, I know the function is increasing. F is increasing because the slope is always positive. On 0 to 1, f is also increasing. And on 1 to infinity, I can say f is decreasing. So I can look at those here. Ready? Here, it's increasing. Between 0 and 1, also increasing. And then decreasing at 1. So this is a possibility. Take a look at B. Between negative infinity and 0, this is decreasing. That's a negative slope. That can't be right. Likewise, C is going to be the same issue. D, let's take a look here. F is increasing. Here we are, F is not increasing. See right here? That's a negative slope again. But here we're saying that F is increasing right here up until we get to 1. So that can't work because this is decreasing, and the answer has to be A. All right, hope you guys enjoyed this video, and I will see you all later. Bye-bye.